Welcome, everybody. So today we're going to talk a little bit about how bar magnets work. And I want to start out by just kind of orienting y'all to where we are. So we've seen a whole bunch of different kinds of magnetic fields produced by different things. Permanent magnets, which we're going to talk about today a little bit. Moving electric charges, which we talked about last week with the Biot-Savart law. Current carrying wire, a current loop. A solenoid, which we'll actually talk about a little bit this coming week. And honestly, the permanent magnet is the toughest of these to write an equation down for. In fact, we probably won't write down an equation for the permanent magnet this term, but I want to think a little bit about how it's going to behave. And to do that, I want to think about what a magnetic field actually does. We saw last week the Lorentz force law, which you can write either for a moving charge or for a current carrying wire. You can see those here. But neither of these expressions helps me understand why a bar magnet does what it does when I, for example, stick it on my fridge or put it next to another bar magnet. So to try to understand what's going on with that, I asked you on your Get Ready activity to think about what's going to happen with these two bar magnets that have their south ends facing each other. And now that you've had a chance to think about that a little bit, I can kind of give away the answer. I'm not even going to do a demo on this one. If I put two south ends of the magnet together, we've already seen, excuse me, from last week, that these two magnets are going to repel each other. And if you let this go for long enough, you might get some more interesting behavior that we'll talk about in class. And to try to understand what's going on here, we're going to introduce a slightly new quantity. And the new quantity is something called the magnetic dipole moment or magnetic moment. Which we'll symbolize with the little Greek letter mu as a vector. Note that this is different from the mu naught, which is just a constant, and you can kind of tell the difference because of the vector symbol. And the magnetic dipole moment is a fundamental property of a bar magnet. It kind of acts just like mass and charge do, right? I can just say, I have an electron. It's got a mass. It's got a charge. Well, it's got a magnetic dipole moment. And so does any kind of permanent magnetic object, like the bar magnets that you would stick on your fridge. If you have a magnet that has a north and a south end, like so, the magnetic moment will always point from the south pole to the north pole. A good way to remember that or conceptualize that is that it will point in the direction that the magnetic field points at the very center of the magnet. All right, so that's this new thing called magnetic dipole moment. We'll be using this in class this week. I'm going to send you back over to Top Hat and give you a chance to think a little bit about what this magnet is going to do if I put it near a current loop.